It is January 24th, 1978. You're standing in the frozen wilderness of the Canadian Arctic. The aurora borealis dances above you, green curtains of light rippling across the black sky. Beautiful, serene. Then the stars begin to move. Not stars, something else. A fireball tears across the horizon, burning brighter than Venus, brighter than the moon. It fragments into pieces, dozens, then hundreds of molten metal raindrops streaking toward the earth. You hear the sonic booms, you feel the ground shake, and somewhere in that brilliant, terrifying light, a nuclear reactor is melting down, not on the ground, not in a power plant with concrete walls and containment domes, in space. A Soviet spy satellite, powered by 50 kilograms of highly enriched uranium, is breaking up in the atmosphere above North America. By morning, the snow will be radioactive. This isn't science fiction. This isn't a nightmare scenario. This actually happened. And if you think Chernobyl was the worst nuclear disaster in history, you've never heard of Kosmos 954. Because while Chernobyl poisoned a region, what happened in the skies above Canada could have poisoned a continent. Welcome to the secret history of nuclear spaceflight and the question that keeps nuclear physicists awake at night. What happens when Chernobyl happens in orbit? To understand how we got here, you have to understand desperation. It's 1965. The space race is white hot. The Americans have shown the world that solar panels work. Tiny silicon cells converting sunlight into electricity, powering satellites for years. Clean, safe, elegant. The Soviets look at solar panels and see weakness. Too fragile, too dependent on the sun. What if you need power in the shadow of the moon? What if you need to operate in deep space, far from the sun's feeble rays? What if, worst-case scenario, you need to power a radar satellite that can track American nuclear submarines through the Arctic ice, 24 hours a day, regardless of weather, regardless of eclipse? You need something denser, something hungrier. You need a nuclear reactor in space. The Soviets called it Topaz. Thermionic experiment with conversion in active zone. A nightmare of uranium and graphite floating 200 miles above the Earth. The Americans experimented with similar systems, the SNAP program, the SP-100, but they were cautious. Too cautious for the Soviets, who were losing the space race and needed a propaganda win. By 1967, the USSR launched Kosmos 100 and IT. It carried a nuclear reactor. It worked. Suddenly, Soviet satellites could carry powerful radar systems that sucked down kilowatts of electricity, power levels impossible with solar panels of the era. They could track NATO fleets. They could listen to radio transmissions. They could watch the American heartland with electronic eyes that never slept. But there was a catch, a deadly catch. These reactors couldn't stay in orbit forever. The uranium fuel, enriched to weapons-grade levels, 90% pure U-235, would eventually decay. The coolant would boil away. The satellite would tumble, and when it did, it would fall. The Americans solved this by designing their nuclear satellites to boost themselves into graveyard orbits, high, stable parking spots where they could circle for 10,000 years far from Earth. Safe, contained, forgotten. The Soviets didn't have that luxury. Their reactors were too heavy, their rockets too weak. So they built something else. The Bezpa system, an ejection mechanism, a poison pill. When the satellite died, it would cough its nuclear core into space, a radioactive brick tumbling through the void, while the satellite itself burned up harmlessly in the atmosphere. At least, that was the theory. January 1978. Kosmos 954 is dying. Launched 9 months earlier, this RORSAT, Radar Ocean Reconnaissance Satellite, is a 2,000-pound monster powered by a uranium-fueled reactor. It's been spying on American naval movements from polar orbit, circling the Earth every 90 minutes, its radar pulses painting the Atlantic Ocean in invisible microwave light. But now it's tumbling. The attitude control system has failed. The satellite is spinning end over end, and the reactor, designed to operate in zero gravity with precise coolant flow, is running hot. Very hot. The Soviets know it's coming down. They calculate the trajectory. They see the nightmare unfolding. The reactor core hasn't ejected. The Bezpa system failed. The entire nuclear payload, 50,000 curies of radioactive material, enough to contaminate a city, is going to re-enter the atmosphere intact, and it's heading toward North America. Moscow sends a coded message to the Canadian government. We have a problem. That's it. No details, no offer of assistance, just a warning that something radioactive is falling out of the sky and it might hit Canada in the next 48 hours. The Canadians scramble. The military mobilizes. They track the decaying orbit using American NORAD data. The predictions get worse by the hour. Instead of falling into the Pacific, as originally planned, atmospheric drag is pulling Kosmos 954 eastward. It's going to come down over the Northwest Territories, some of the most remote, pristine wilderness on Earth. On January 24th at 11:53 GMT, Kosmos 954 hits the atmosphere. What follows is chaos. The satellite breaks apart over Great Slave Lake, scattering debris across a 600-kilometer path. The reactor vessel, designed to survive re-entry heat, shatters. Uranium fuel rods vaporize. Radioactive dust rains down across the frozen tundra. Operation Morning Light begins. A joint Canadian-American team parachutes into the Arctic in the dead of winter. Temperatures hit -40 degrees. The radiation is invisible, odorless, and deadly. They wear dosimeters that scream when radiation levels spike. They search on foot, on snowmobiles, from helicopters. They find the first piece on January 26th, a jagged chunk of the reactor core, lying in the snow, hot enough to melt the ice around it. The Geiger counters go crazy. The reading is 200 Roentgens per hour, a lethal dose in 2 hours of exposure. The cleanup takes 8 months. They find 12 large pieces of the reactor, but only 1% of the nuclear fuel. The rest, 49.5 kilograms of enriched uranium, is gone, vaporized. Spread across the Canadian shield in particles too small to see, too widespread to collect. The Canadians bill the Soviets $6 million for cleanup costs. The Soviets pay $3 million and call it even. The world moves on. But the lesson is etched into the minds of space policy experts. Nuclear reactors in low orbit are ticking time bombs. And Kosmos 954 wasn't the last one. 4 years later, it happens again. December 1982, Kosmos 1402, another RORSAT with another nuclear heart, begins tumbling. This time, the Soviets are prepared. They trigger the Bezpa system. The nuclear core ejects into a higher orbit. Safe, they think, for 600 years. They're wrong. The core's orbit decays faster than calculated. 6 weeks later, in January 1983, the reactor comes down over the South Atlantic. It burns up completely, they claim. No debris found, but radiation detectors on spy planes pick up a spike in atmospheric radioactivity over the Indian Ocean. The core didn't burn up cleanly, it scattered. Then comes Kosmos 1900 in 1988, another RORSAT, another failure. This time, the core ejects successfully, but the satellite itself, still containing radioactive coolant and secondary materials, comes down over land. By the late 1980s, the Soviet RORSAT program has launched 33 nuclear-powered spy satellites. 1 in 3 has experienced catastrophic failures. The odds are worse than Russian roulette. But the real terror isn't the accidents that happened. It's the accident that almost happened. The one that would have made Chernobyl look like a minor spill. Imagine it's 1985. The Cold War is at its peak. Reagan is in the White House. Chernenko is dying in the Kremlin. And Kosmos 1687, a massive RORSAT with an upgraded Topaz 2 reactor, is circling the Earth with 100 kilograms of enriched uranium. Something goes wrong. Not a gradual decay, but a catastrophic failure, a micrometeorite strike perhaps, or a coolant pump seizure, or a military command to change orbit that overloads the reactor. The satellite doesn't tumble gently, it explodes. Not a nuclear explosion. Uranium reactors can't detonate like bombs, but something almost as bad. A steam explosion, like Chernobyl Unit 4. The pressure vessel ruptures. The reactor core is exposed to vacuum. Molten uranium, operating at 1500 degrees Celsius, meets the cold of space and shatters into droplets, thousands of them, each radioactive, each in a slightly different orbit. This is orbital Chernobyl. Instead of falling in one place, the debris spreads across the entire orbital shell. Each droplet becomes its own satellite, circling the Earth every 90 minutes, passing through the altitude where the International Space Station will one day fly, where commercial satellites operate, where astronauts walk in space. The radiation signature is detected immediately. American early warning satellites, designed to spot nuclear launches, see the thermal bloom. NORAD tracks the debris cloud. Within hours, there are 500 pieces larger than a softball, each glowing hot on infrared, each carrying enough strontium-90 and cesium-137 to classify as a dirty bomb. But they can't predict the orbits. The explosion has injected debris into elliptical paths. Some pieces will decay in months, burning up in the atmosphere. Others will stay aloft for centuries. And as they decay, they spread. 2 weeks after the explosion, the first piece hits the atmosphere. It comes down over Buenos Aires, a lump of graphite moderator the size of a basketball, still hot, crashes through a warehouse roof. The radiation burns a meter-wide circle into the concrete. Panic ensues. 3 days later, another piece, this time a fuel rod fragment, lands in the Australian outback. A sheep station is evacuated. The sheep are slaughtered. The land is quarantined for 10 years. But the worst is yet to come. 6 months after the explosion, a piece the size of a car engine comes down over the Atlantic. It misses land, but it doesn't miss the container ship below. The impact triggers a secondary explosion, chemical, not nuclear, that spreads radioactive debris across 20 square kilometers of ocean. The shipping lane is closed. Insurance companies declare force majeure. Global trade suffers a billion-dollar hit. And the cloud? The fine particles, the ones that didn't fall immediately, they form a ring around the Earth. Like Saturn's rings, but made of uranium dioxide dust. Solar panels on satellites begin to degrade as the dust impacts them at 17,000 miles per hour. Spacecraft face increased radiation hazards. The Hubble Space Telescope, still on the drawing board, would have its mirrors pitted by microscopic radioactive particles. This is what orbital Chernobyl looks like. Not one disaster, but 1,000. Not contained to a 30-kilometer zone around Pripyat, but distributed across the entire planet, random, unpredictable, lasting for decades. And in 1985, we were one malfunction away from this reality. But there's a darker chapter, one that was classified until 1992. The Soviets didn't just launch RORSATs, they had plans for manned nuclear spacecraft. The TMK heavy interplanetary ship was designed to carry 3 cosmonauts to Mars. It would be powered by nuclear electric engines using the same Topaz technology, scaled up by a factor of 10. The mission was scheduled for 1980. It never flew, but the prototypes were tested in orbit. Kosmos 434, launched in 1971, carried a nuclear engine. Kosmos 11818 tested a new reactor design in 1987. These weren't just test beds, they were proof of concept for a fleet of nuclear-powered space tugs, massive vehicles that could move cargo around the solar system, build space stations, mine the asteroids. And they were assembled in orbit by cosmonauts. Imagine the scene. It's 1988. 2 Soviet cosmonauts are performing an EVA, extravehicular activity, 300 miles above the Earth. They're wearing bulky Orlan suits, tethered to the Mir space station, Between them floats a cylinder the size of a Volkswagen Beetle. It's the NPS, nuclear power source, for a new generation of spy satellites. They're installing it by hand. The reactor is cold, not yet activated, but it still contains enriched uranium. The radiation levels are low but not zero. The cosmonauts have dosimeters clipped to their suits. They work in 20-minute shifts because that's the maximum safe exposure time. One of them, let's call him Sheldon 327 because his real name is still classified, bumps the reactor with his glove. A fuel rod, not fully secured, shifts. The radiation detector spikes, not to lethal levels, but to career-ending levels. He's already absorbed his yearly dose in 30 seconds. He finishes the installation anyway, because if he doesn't, the reactor tumbles away, uncontrolled, a hazard to navigation. He saves the mission. He sacrifices his future health. Sheldon 327 dies of leukemia in 1997. He's buried in a lead-lined coffin in an unmarked grave outside Baikonur. The official cause of death is natural causes. He never existed. His mission never happened. This is the human cost of nuclear spaceflight. Not just the victims of accidents, but the workers, the liquidators of the high frontier, who absorbed radiation so that satellites could keep spying, so that Mars missions could stay on schedule, so that the Soviet Union could keep pace with a race that was bankrupting both superpowers. But the worst near miss isn't from the Cold War. It's from 1996, November 16th, 1996. The Mars 96 probe, Russia's most ambitious planetary mission, launches from Baikonur. It's carrying 200 grams of plutonium-238, packed in 4 radioisotope thermoelectric generators. Not a reactor, just the heat from decaying plutonium converted to electricity. Safe, stable, proven technology. The mission is doomed from the start. The 4th stage of the Proton rocket fails to fire correctly. Mars 96 doesn't escape Earth's orbit. It enters an elliptical trajectory that will bring it back to Earth in a matter of hours. The panic in Moscow is absolute. If the probe re-enters, the plutonium will scatter. Not as bad as uranium. Plutonium-238 is an alpha emitter, not gamma, but bad enough. A single microscopic particle inhaled into the lungs causes cancer, and there are 200 grams of it. Billions of particles. The Russians try to trigger the destruct sequence. No response. The probe is tumbling, out of control, carrying enough poison to contaminate a province. It comes down on November 17th, somewhere over the Pacific Ocean. Or maybe Chile, or maybe the Andes. To this day, nobody knows exactly where Mars 96 crashed. The beacon never activated. The wreckage was never found. Some experts believe it crashed in the ocean, sinking to the bottom where the plutonium is contained by water pressure and corrosion. Others think it came down in the remote mountains of Bolivia, where the wreckage lies frozen in a glacier, waiting for climate change to thaw it out and release the poison. This is the legacy of nuclear spaceflight: lost bombs, wandering reactors, and the nagging certainty that somewhere out there, in the wilderness or the deep ocean, there's a piece of the space age that's still radioactive, still dangerous, still waiting. You might think this is history, that we learnt our lesson, that nobody puts nuclear reactors in space anymore. You'd be wrong. In 2018, Vladimir Putin announced the Zeus project, a nuclear space tug designed to carry heavy cargo to the Moon, Mars, and beyond. Not RTGs like Mars 96, a full reactor, a megawatt-class nuclear electric propulsion system 10 times more powerful than anything the Soviets flew. The Russians aren't alone. NASA is developing the Draco mission, demonstration rocket for agile cislunar operations, a nuclear thermal rocket scheduled to fly in 2027. China has tested nuclear reactor prototypes for their planned moon base. India, France, and Japan all have active nuclear space propulsion programs. The technology is coming back. But the world has changed. We don't have the empty orbits of the 1970s anymore. Low Earth orbit is crowded. There are 8,000 satellites up there. The International Space Station houses astronauts 24/7. Commercial space stations are being built by SpaceX, Blue Origin, and Axiom. The Moon is becoming a destination, not just a waypoint. If a nuclear satellite fails today, it doesn't fall on empty tundra. It falls on the information economy. It threatens the GPS that guides your Uber, the weather satellites that predict hurricanes, the relay stations that let you watch this video, and the worst-case scenario. It's worse than ever. Modern nuclear space tugs use different fuel. Instead of highly enriched uranium, some designs use weapons-grade plutonium or even thorium. But the most dangerous, the ones being developed for Mars missions, use high-assay low-enriched uranium, HALEU, enriched to 19.75%. That's just below weapons grade, safe for proliferation, but still hot. A Mars transfer vehicle might carry 500 kilograms of HALEU. If that explodes in orbit, it doesn't just create a radiation hazard, it creates an exclusion zone in space. Imagine a debris field, radioactive and dense, orbiting at the exact altitude where all satellites must pass to reach geostationary orbit. A minefield in the sky, a barrier that could trap us on Earth for centuries. This isn't science fiction. This is the calculation that space lawyers are making right now at the United Nations Office for Outer Space Affairs. How do you regulate nuclear materials in orbit? Who is liable when a Russian reactor falls on Canada? Who pays for the cleanup when an American Mars ship explodes over Europe? There are no good answers, only the physics of decay, the mathematics of orbital mechanics, and the cold reality that nuclear power and space exploration are locked in a deadly embrace we cannot escape. So why do we do it? Why play Russian roulette with the high frontier? Because without nuclear power, we don't go to Mars, full stop. Solar panels work fine near Earth, but Mars is 50% farther from the Sun. A solar array that generates 100 kilowatts in Earth orbit generates only 40 kilowatts at Mars, and that's during the day. During dust storms, which can last months, output drops to near zero. If you want to keep astronauts alive on Mars, heating their habitat, recycling their air, powering their rover, you need nuclear. A 40-kilowatt reactor weighs less than a solar array of equivalent power, works day and night, and laughs at dust storms. For deep space probes, missions to Jupiter, Saturn, the ice giants, solar is useless. The Juno probe at Jupiter carries massive solar panels the size of a basketball court. At Saturn, they'd need to be the size of a football field. At Neptune, you'd need panels the size of Manhattan. Nuclear is the only way. But the risk is orbital Chernobyl. It's the scenario we almost saw in 1978, in 1982, in 1996. It's the nightmare of a reactor core, glowing blue with Cherenkov radiation, tumbling through the darkness, waiting to fall. And the longer we wait, the worse it gets. The debris in orbit is already a problem. The Kessler syndrome, the cascade of collisions that turns orbit into a shooting gallery, is a real threat. Add nuclear materials to that mix, and you don't just have broken satellites. You have broken radioactive satellites. Shrapnel that glows in the dark. This is the choice we face: Earthbound safety or nuclear-powered expansion. There is no third option. There is no solar panel that works in the outer solar system. There is no battery that lasts 10 years. There is only the atom, split and harnessed, floating above our heads. Let's personalize this. Let's stop talking about statistics and scenarios and talk about people. When Kosmos 954 fell, the cleanup crews were Canadians. Reservists mostly. Kids in their 20s who joined the military for college money. They were handed Geiger counters and shovels and told to dig uranium out of the permafrost. They wore dosimeters. They rotated out when levels got too high, but too high is relative. Some of those soldiers absorbed 25 rem in a summer, more than nuclear workers are allowed to absorb in 5 years. 20 years later, cancer rates in that cohort were elevated. Not dramatically, but measurably. The Canadian government settled lawsuits quietly in the 1990s. The Soviet cleanup crews, the ones who dealt with Kosmos 1402 and the others, were mostly conscripts. Some were radiation specialists from the Chernobyl cleanup, already damaged, sent to handle space accidents because their careers were over anyway. They called themselves liquidators, same as the Chernobyl heroes. They were issued cheap vodka after shifts, not for morale, but because alcohol is a diuretic. It makes you urinate. It flushes isotopes from your system faster. That's how you treat radiation poisoning on a budget. You get the men drunk and hope they piss out the strontium before it settles in their bones. Nobody knows how many died. The Soviet Union collapsed before the studies could be completed. The records vanished into the archives of Roscosmos, sealed until 2070. But we know this. Every nuclear satellite that has ever failed has left a footprint, a hot spot in the snow, a contaminated valley, a statistic in a cancer registry. And the next one, the big one, the orbital Chernobyl that we hope never comes, won't just kill the cleanup crews, it could kill the space age itself. Here's the scenario that truly terrifies orbital mechanics experts. It's 2035. A nuclear space tug, maybe Russian, maybe American, maybe Chinese, is moving cargo to lunar orbit. It carries 300 kilograms of HALEU fuel. It's passing through low Earth orbit, transiting the most crowded altitude band, 400 to 800 miles up. A piece of debris, old satellite maybe, or booster remnant, strikes the tug. Not a direct hit on the reactor, but close enough. The fuel tank ruptures. The reactor scrams, shuts down, but the fuel is exposed. The containment vessel is breached. The tug explodes. Not nuclear, but chemical. The propellant tanks go up. The explosion fragments the vehicle into 10,000 pieces, each moving at orbital velocity, 17,500 miles per hour. One of those pieces hits a Starlink satellite. That satellite hits another. The chain reaction begins. This is Kessler syndrome, the theoretical cascade where one collision creates debris that causes more collisions. But this debris is radioactive. Within hours, the debris field spreads across the polar orbits. It intersects with the International Space Station. The crew has to evacuate, but the evacuation capsules have to pass through the debris field to get down. Within days, 20% of all satellites in low Earth orbit are disabled. Some by direct impact, others by radiation damage to electronics. Solar panels on the ISS are pitted and cracked, unable to generate power. Within weeks, the radiation has decayed enough that the immediate hazard is gone, but the debris remains. Thousands of fragments, each tracked by NORAD, each a bullet waiting to hit something. The orbit is unusable, clogged with radioactive shrapnel. We can't clean it up. We don't have the technology to deorbit that much debris, especially when it's hot. We have to wait for it to decay naturally, which takes years, decades, centuries depending on the altitude. During that time, no satellite can pass through, no space station can be built, no mission to the Moon or Mars can launch because they all pass through low Earth orbit first. We are trapped, earthbound, the high frontier closed by our own hubris, by our need for power, by the physics of the atom. This is the true legacy of orbital Chernobyl. Not a single explosion, but a locked door. A future denied. There is one final piece to this puzzle. The law. When Kosmos 954 fell on Canada, the Soviets paid $3 million, but that was a goodwill gesture, not a legal settlement. Under the 1972 Liability Convention, spacefaring nations are absolutely liable for damage caused by their space objects on Earth, but the convention has never been tested in court. Nobody knows if it applies to nuclear materials specifically. Who is liable if a nuclear space tug explodes in orbit and disables a commercial satellite? The launching state, the manufacturer, the operator. What if the debris falls on a neutral country? What if it falls in international waters? What if it causes a nuclear incident, a scattering of fissile material that triggers a panic but no immediate deaths. There is no framework for this. The Outer Space Treaty of 1967 bans weapons of mass destruction in space, but it doesn't ban nuclear power. The Nuclear Test Ban Treaty doesn't apply to space accidents. The International Atomic Energy Agency has no jurisdiction over orbital reactors. We are operating in a legal vacuum, launching nuclear materials into orbit based on gentlemen's agreements and technical standards that were written in the 1980s. Russia is building Zeus. NASA is building Draco. China is testing prototypes, and nobody has updated the liability laws since 1972, when there were 10 satellites in orbit, not 10,000. This is madness. This is driving at 100 miles per hour with no seatbelts, no speed limits, and no insurance. Sooner or later, someone crashes, and when they do, the lawyers will discover that the law hasn't caught up to the physics. So here we are, standing at the edge of a new space age, holding a nuclear match. On one side, Mars, the asteroids, the outer planets. A future where humanity is multiplanetary, where we mine the resources of the solar system, where we become a Type 1 civilization harnessing the energy of entire planets. On the other side, orbital Chernobyl, the Kessler Cascade, the radioactive debris field that traps us on Earth for centuries. We cannot have one without risking the other. Nuclear power is the only technology that can get us to Mars with current physics. But every nuclear rocket we launch is a potential disaster. Every reactor in orbit is a potential cascade trigger. The Soviets rolled the dice 33 times with RORSATs. They got lucky. Most of the cores ejected successfully. The ones that didn't fell in remote places. We won't be that lucky forever. The orbits are crowded now. The margin for error is gone. The question isn't if anymore, it's when. When will the next Kosmos 954 fall? When will the next Mars 96 vanish into the ocean? When will the first nuclear collision trigger the cascade? And when it happens, will we be ready? Will we have the cleanup protocols, the liability frameworks, the emergency response teams? Or will we watch, helpless, as the sky rains fire and the space age ends not with a bang, but with a Geiger counter's scream? The sun is setting over Baikonur. It's 1978 again. Kosmos 954 is burning up somewhere over the horizon, and a Canadian reservist is staring at a chunk of Soviet engineering glowing in the snow, wondering how the Cold War became so hot, so fast, so radioactive. He picks up his shovel, he checks his dosimeter, he starts digging. Because that's what we do. We clean up our messes, we face the consequences of our ambition. We go to the stars because we must, even knowing that the path is littered with our failures. But we go smarter, we go safer, or we don't go at all. Because the next Chernobyl won't be in Ukraine. It won't have a concrete sarcophagus. It won't stay where it fell. The next Chernobyl will be moving at 17,000 miles per hour, overhead, every 90 minutes, waiting to fall. And when it does, there will be no evacuating the planet. This is the price of the high frontier. This is the risk of the atomic age. This is the legacy of every nuclear satellite ever launched, every reactor orbiting overhead, every dream of Mars powered by the splitting atom. We have 8 minutes to live. Let's make them count.